we should have out our practice final pages 4, 5, and 6. And let's go ahead and take some time and review these. And as questions arise, I have camera ready, note paper ready, and be happy to explain what needs to be clarified, if anything needs to be clarified. All right, so starting with question number 50. Question 50 says that an LED requires 15 milliamps at 1.4 volts connected to a power supply. Series limiting resistor is shown as part of the circuit. The power supply set to 6 volts. What resistance would you specify for the limiting resistor? And that limiting resistance comes in at what value, Luis?
I actually missed this one.
Okay, that's all right. We'll get the question would then go to Jess. Do you happen to have this one?
No, I actually haven't got any of these done yet.
Okay, then let's take a look here. Next, Harpreet.
Yes, 306.67 ohms.
306.67 ohms is correct. Okay, 306.67.
Would you mind explaining this one?
Yes, this one's, the word exercises are really fun, and they're, you have to read it. And as you read it, you want to write down what it is that you are reading. So let me go ahead and do this. Get this guy set up. Let me go to here. Let me go to here. And this way. Good. All right. So, and focus. Good. Okay. So as we look at this particular exercise, we happen to have a circuit, power supply, LED, and a series resistor. The best way of reconciling any kind of a word exercise is to draw the schematic. So in your schematic, you see a power supply, you see a DC power voltage source here, yeah? In your schematic, in your drawing, you have a resistor and an LED. So in your schematic, you put in an LED and you put in a resistor. Now, keep in mind, the polarity of the LED is very specific. Remember that when you built your LEDs in your circuit boards, if you wired the LED backwards, it would not light up. So here in this particular case, let me go ahead and speaker view so you can see this in greater detail. So is this a little larger where everybody can see better now? All right, so now that being said, so you draw the schematic, and so you want to make sure that if this side of the source is positive and this is negative, then this side of the LED is positive, this side is negative, positive and negative. Those would be the polarities around the LED and the resistor. So it tells you flat out that the LED requires 15 milliamps at 1.4 volts. It tells you flat out that's what you have. So you can always solve this using a VIR. And you can do it this way for an R for the LED and for the total. Do it this way. And you are told for the LED, you happen to have 1.4 volts. And you are also told that it takes 15 milliamps. You are also told that your voltage supply is 6 volts, yeah? So on your VIR chart, if you got a 6 volt total, the LED takes 1.4. How do you find the voltage for your resistor? What do you think? Don't you take the 6 volts and you minus the 1.4, and won't you get the 4.6 volts that I wrote over here? That's how you find the voltage across the resistor. So you start with knowns. You start with the facts. 6 volt source, 1.4 volts for the LED, 15 milliamps for the LED in order to make this work. We don't care about the resistance of the LED. We are interested in the ohms of the resistor. So are we clear that 6 minus 1.4 gives you 4.6 volts on the resistor? Now, once you have that, since this is a series circuit, what is the same through all parts of a series circuit? Isn't current the same through all parts of a series circuit? So if you're told 15 milliamps is flowing through the LED, isn't that 15 milliamps through the total? And isn't that also 15 milliamps flowing through the resistor. It's a series circuit. So those are the pieces of your puzzle. You now know right here in my drawing, 4.6 volts for the resistor, divide by 15 milliamps, and that's how you end up with the 306.63 ohms. Is everybody okay with how this is done? The key to how this is done, first of all, is to draw the schematic. Next part of the key of how it's done, you can always rely on your VIR chart for the key things, okay? And any further questions on number 50? We good with number 50? All right. Let's go into the next one. So the next one, given this schematic that's shown here, calculate one time constant. So we are looking for one time constant. So let's see. Carlos Navarro, do you have a time constant for number 51 for me?
I do not actually need help with that one.
Well, it's R times C is how you calculate time constant. Do I have an R? Do I have a C? Pop these numbers into your calculator. 10K times 100 microfarads. And you'll calculate a number. Toan, what number do you have?
1 second.
It works out to be 1 second. So 1 second is the correct answer for the time for one time constant. So the next question is, you are asked for how long will this therefore take for this cap to reach full charge? So Abbas, how long will it take for this cap to reach full charge?
$11.25 kilojoules.
We're on question 51. The 52. We're on 52.
Yeah, I thought it would be that, but I guess not.
All right. If we review the concept of time constants, my friends, time constants, if I draw the graph looks like this, and I have 5. So 0 tau, 1 tau, 2 tau, 3 tau, 4 tau. The symbol that looks like an italicized T is TAU, and I have 5 tau. And so tau is calculated as R times C, which when we multiply 10 k ohms by 100 microfarads, we end up with 1 second of time. So that means between here and here, within the time span of 1 tau, you have 1 second of time that is spent for this thing to charge up to, remember the charging cycle for a cap looks like this. So it will reach 63.2% after the first tau, and then progressively climbs up until it reaches full charge. That being said, let's go back. Greg, if one time constant is 1 second, how long will it take for the cap to reach full charge?
5 seconds.
Precisely, because it's 5 tau. We say the full charge is equal to 5 tau. And if 1 tau is this, all you have to do, if 1 tau is 1 second, all you have to do is multiply by 5, and you're going to get 5 seconds. Okay?
Okay, thank you.
You're welcome. Next question is number 53, having to do with the capacitor. What is the value of capacitance for number 53? Javier.
47,000 picofarads.
47,000 picofarads. Punch that into your calculator. That's not proper engineering notation. Yeah, this is your intermediate value. I write down 47,000 picofarads, but that's not what I would put on the answer sheet.
47 nanofarads.
There you go. Good job. It's 47 nanofarads, my friends. Is everybody clear? Remember how to decipher capacitor values. First digit of the code is the first digit of the value. Second digit of the code is the second digit of the value. The third digit of the code is number of zeros. So after I write down the 4 and the 7, I write down 3 zeros, and it's always going to be in units of picofarads. You key this into your calculator, guaranteed you will have 47 nanofarads. Okay? Okay. Next, based on this new capacitor, you are asked to calculate one-time constant with the original 10K ohm resistor. So now you're going to multiply this value of C times this value of R. So for number 54, Anna, do you have this value for me?
2.35 milliseconds.
We're on number 54, dear. I think you gave me the answer for 55. We want one-time constant.
70 microseconds.
Yeah, so this would work out to be 470 microseconds. If I multiply the 47 nano to the 10K, I will have 470 microseconds. Then, that's one-time constant. Now, in order to calculate full charge, you have to bring in 5-time constants. So instead of this being 1 second now, this is now 470 microseconds. This is another 470 micro. This is another 470 micro. So you could add up 5 of these, 470 micro, another 470 micro, or you just simply do 470 microseconds and you multiply that by 5. And what is the answer that you get off of this, Harpreet? What's the time for full charge if we change the capacitor to a number 473 cap?
I'm calculating. .35 kilo ohm.
Well, first of all, time is not measured in ohms.
2.3 kilohertz.
Time is not measured in hertz. Frequency is measured in hertz. Jess, what do you have?
I have 2.35 milliseconds.
And the answer is 2.35 milliseconds. Time is measured in some units of seconds, and that is a 10 exponent negative 3 is not a 10 exponent positive 3. If you wrote down 2.35, anything else other than milliseconds, that answer would be half wrong. Okay, so be careful of your units of electrical quantities and time. Frequency is in hertz, time is in seconds, and all the electrical quantities you should know. Okay, next question, number 56, asks you, what is the control that you would use to have fewer cycles displayed on the screen? And that question would go to Tony. What do you have?
Time base.
Time base is correct for number 56. Time base is correct for number 56. Number 57.
Professor, I have a question for that.
Yes, yes, please.
If I wrote down SDiv, is that okay?
SDiv, yes, certainly. It means the same thing. Yes.
Okay.
Seconds per division is the same as time base. Yeah. And that's why I have to look at what you write down. Yeah, so my seconds per division. What your classmate was asking was, could we write down S per division? And that would be the same meaning as time base. Okay, very good. Next, question number 57. 57, Tawan, help us out here. What is the control to see taller cycles, taller waveforms on this screen?
Vertical.
That would be the vertical control. Vertical is correct. Okay, very good. The next question, why might electrolytic capacitors cause a shock hazard? The question would go to, let's take a look here, Ryan. How would electrolytic capacitors cause a shock hazard?
I said they could cause a shock hazard by continuing to give off voltage after the power source has been shut off.
That is precisely what would happen when you turn off first of all, you have the capacitor is charged and it's able to hold a charge for a period of time. And so the shock hazard is, even though you remove the charging source, the voltage source that would charge the capacitor, because it can hold a charge for some time, it can still give you a shock, okay? It stores charge between the conductive plates and it can give you a shock. Any more questions on page 4?
Yeah.
Yes.
Is it the electrolytic capacitors that also could have a shock before they've ever been used because of static buildup?
That would be really unusual for that to happen.
Okay.
Static would occur by freeing electrons. And so if I have a capacitor that, let's say for a moment, pretend for a moment, this is a capacitor. Now we can see it's a 9-volt battery, but let's pretend for a moment it's a capacitor. I charge it up, it holds a charge. If I touch it, I'll get a spark. But if I discharge it by putting a resistor between the two, and this thing's now discharged down to nothing, wherever I leave it, unless I do something to this capacitor, it won't charge itself. In order for static charges to happen, free electrons have to be freed, and you already know it takes energy in at least 7 different forms to create free electrons. And as long as I don't expose this to light, it's not sensitive to light. As long as I don't expose this to friction, heat, applied magnetic fields, chemical, pressure, any of the other ways that we've talked about for freeing electrons, this will not build up a charge on its own. It has to be connected to some sort of a voltage source in order for it to be recharged. Okay?
Are there any other types of capacitors that are at a risk for that? Because I remember I was reading about capacitors, and I think one of the things I had read mentioned that some capacitors are susceptible to having a bit of a charge.
And there won't be enough to cause you injury. It won't be what we would call a shock hazard.
Oh, okay.
Yeah. Okay. So for a shock hazard to occur where you'll actually feel it, an electrolytic capacitor is what's going to do that. Good question. Any other questions on page 4?
I had a question on that one as well.
Yes, please.
So an electrolytic capacitor as opposed to what kind of capacitor?
Oh, a ceramic capacitor, any of the plastic capacitors, like a polypropylene mylar capacitor. Those capacitors are passive devices, and they don't hold the charge quite the same way that an electrolytic does. Can they store a charge? Yes, they can store a charge, but they won't cause you any kind of a shock hazard, much the same way that an electrolytic would.
Okay. And do electrolytic capacitors pose more of a threat because they have the thin insulators and the dielectric that leaks out?
The dielectric won't leak out like a carbon zinc battery leaks, but what will happen with capacitors is, yes, they still can leak over time. And generally, we find leaky capacitors occur in large power amplifiers in sound systems. So the large capacitors in sound systems are about the size of a small soda can, and they, over a period of time, can leak. So we can see some discharge oozing that has oozed out. It won't actively be oozing like lava, but it will have oozed out over time, such that when we look inside some of the larger audio amplifiers, we look at the circuit board upon which the capacitors are mounted, we may see some kind of corroded residue around the base of the cylinder of the cap. So imagine this is a cap and it's sitting on the circuit board, we would see around its periphery some kind of corrosive looking material, and that would be indicative of a capacitor that has leaked.
I see.
Mm-hmm.
Okay.
Good. You're welcome. Any other questions on page 4? Okay, page 5. So as we look at page 5, interesting, I posted this at least 3 times, what the value of the resistor was, and people keep asking the question. You got to use Discord in a you just got to use Discord because we use it as a communications device for quick questions that people ask. You all get pinged on Discord when something happens. So just peek and scroll up. If you scroll up, you'll see a question somebody had asked. So who still does not know the resistor value for the circuit?
I do not.
Okay. It is intended to be 15 kilo ohms. And yes, it was posted 3 times. That's all right. So as this is 15 kilo ohms, your job was to reconcile whatever this asked you for. And let's see, what was the question on this one? Oh, it asked you for the total voltage and it asked you for total current. So the total voltage on this particular guy, Chisamaga, what's the total voltage on this guy? I got a 12 volt source, I got a 10 volt source, and now we find out it's a 15K ohm resistor.
I put 2 volts.
Well, I got a 12 and I got a 10. How do you reconcile the two?
Well, aren't they series opposing?
Very good. I'm just looking for a verbalization. They are, in fact, series opposing. The VS1 wants to move electrons in a counterclockwise fashion, while VS2 wants to move electrons in a clockwise fashion. So might is right. This one's bigger. It will overwhelm this one, and the difference between the two is, in fact, 2 volts. Okay? And then so knowing that you have 2 volts with a 15K ohm resistor, your calculation of current, Erica, what's your calculation of current on this?
I got 133.33 microamps.
Excellent. It's 133.33 microamps, not milliamps, not kiloamps, micro. And it is amps, not ohms, not watts, not hertz, not seconds. So please be very mindful. Just because you crunch out a number doesn't mean that's all you put down. You have to be mindful of the engineering, the appropriate engineering prefix, that this is proper engineering notation, and the necessary electrical quantity or frequency or hertz, frequency or seconds, depending upon what the question's asking for. Okay, next one, number 50, oh, number 60. This is a good one, yay. So here, we venture more in the area of series aiding or series opposing. So the very first question that you're asked is, what is my voltage total on this particular guy? So voltage total on this particular guy, question will go to Ephraim.
Yes, what number was it? Sorry.
Number 60.
60. I have 24 volts.
24 volts, because these are series opposing. Might is right. What that means is the bigger one will subtract the smaller one. So 34 take away 10 will give you 24 volts. Everybody okay with the total voltage? Then the next question that you're asked for is total ohms and then total current. And so the total ohms with the total current, that information will come from, let's take a look here, Luis. What's my total ohms and what's my total current?
Total ohms, I got 12 ohms.
12 ohms is the total ohms, and what's my total current?
Total current, I got 2 amps.
2 amps would be correct, okay? Total ohms and 12 ohms and 2 amps. Any questions on that? Okay. Now, the next question, which you will see some variation of for sure next week, will be your phase shift. This happens to be phase shift analysis with respect to a resistor capacitor combination, and you know the code guy is not going to give you a capacitor value. The code guy is going to give you a code. What do you do with the code? You have to decode it to find the capacitor value. So you are shown a 373. How do you decode 373 into a capacitance value? Frank Sepulveda, how do we do this? Francisco, I know you're there. How do we do 373 into a capacitance value?
Sorry, I'm in a car right now driving.
Oh, heavens.
I'm sorry.
No. Drive safely. It's all right. It's all right. Don't
Yeah, I
apologize.
accidentally hit the wrong button, so my camera turned off. But,
Well, yeah, we don't want you to get into an accident, so just continue driving safely. We'll catch up with you later. It's quite all right. Just be sure to catch up on all of this later. Abbas, what do I do with the 373, Abbas? Unmute your mic so we can hear you.
Sorry, I didn't get that one.
Okay, we're going to be looking at capacitor values. They're going to be all over your final next week. So the key question is, do you recall how to decode a capacitor value? We did it earlier on the previous page.
Decode the 373?
Yeah, into a capacitance, yes.
Okay, so 373 is you take the first number, which is a 3, which is going to be a 3. You take the second number, 7, and the third number tells you how many zeros there's going to be after it, which is 3 zeros.
Okay, then what?
Then you put it into 3700. I think is it pica or is it like?
It's picofarads.
Okay, picofarads.
Mm-hmm.
And so then after you put that into your calculator, hold on, let me no.
Okay. You coded this into the calculator, so what do we write down on our answer sheet?
37. Wait, what's it? 20. Exponent 27. What is that?
It's not an exponent 27, I guarantee you. Okay, here, let me help you out. We have a calculator, yeah?
Yeah.
And we type in 37 with 3 zeros. Pico is what power of 10?
Negative. Oh, it's negative 12.
Well, then that's what we need to do. So on my calculator, I am going to hit exponent negative 12. So there's my 37,000 exponent negative 12. And now all I have to do is hit the equal key and engineering. And what does my calculator and your calculator show you?
Calculator shows me 37 exponent negative 9, which is nano.
Okay, so read off the entire answer.
37 nanofarads.
Nano what?
Nanofarads?
Nanofarads, precisely. So this gives you 37 nanofarads. All right, so on a test next week, you should be able to do this more fluidly because we have a lot of things to do, okay? So definitely practice capacitor values. How can you practice capacitor values more? Get on with your study group and just shoot different numbers, different 3-digit code numbers to each other. So here's an 842. Here's a number 571. Just make up 3 numbers and just code them and have everybody in the study group decode them and see if you have a consensus of opinion. And that's how you're going to be able to get all the practice you need for next week. Okay? All right. That's my suggestion. Yes.
I have a question about decoding the capacitors.
Yes.
I remember reading that there's the standard units for farads are the farads, microfarads, or picofarads. So are we going to be required to notate them in that way?
No, not for the first semester. We will fine tune our understanding of the exceptions to proper engineering notation in the later classes. But for the time being, if I can get my students to decode the value so that it's 37 nanofarads, I'm pretty darn happy with this.
Okay.
The industry standard, of course, is 0.037 microfarads because the industry standard is to have these 3 categories. Let me write this a little more clearly. Microfarads, picofarads, or farads. Those are the standardized units of which capacitors are specified. And so since nanofarad is not a standardized unit, we have to go to one of these, and the closest one of these that will be used will be 0.037 micro. But that is a fine distinction we're going to say for other electronics classes. I'm just very, very happy if we can get to this, because this 37 nano is a very workable number that will help us solve everything else. So I purposely did not include this extra rule that for first semester, we don't need for first semester. Did that answer your question, Jess?
Yeah, perfect. Thank you.
Okay, that was a good question. I appreciate it. Okay, so next, so what we have to solve for based on this is, let's see, first thing we ask you is, what is my V in peak? So the V in peak for this particular guy, Harpreet, what's my V in peak? What's the very first answer on the bottom of the sheet?
I don't have that one.
Well, take a look at what's specified, and you can use Mama's math to figure this one out.
Sure.
What's my voltage source show?
20 volts.
No, it doesn't show that. What do you read this completely? What's it show? What am I pointing at?
Yeah, VPP.
It's peak to peak.
It's 20 volts peak to peak.
Okay.
It doesn't just show you 20 volts. It shows you 20 volts peak to peak.
Okay.
It's very specific what it shows you. So given that it shows you 20 volts peak to peak, the first answer is, what is my V input peak?
It'd be 10.
10 what? Apples? Oranges?
10 volts.
10 volts what?
10 volts peak.
There you go. Now that's a complete answer. Whew. All right, you guys. Here we go. There's your waveform, yes? And it is specified in no uncertain terms on the drawing that you have a 20 volt peak to peak. It doesn't say RMS, it doesn't say single P, it doesn't have anything missing behind the V. It says 20 volt peak to peak. So that means from here down to here is 20 volt peak to peak. The very first question that's being asked of you is, how much is coming into the circuit, and the input's over here and the output's over here. How much is coming into the circuit, and it's asked of you in this form, volt peak. So if my input's 20 volt peak to peak, what is my volt peak? Mama's math says it's going to be half, right? 10 volt peak.
Professor, I don't understand the notation on the worksheet where it says VIN peak. What is that supposed to mean?
V input. V
Okay.
input, and you have V out. So what goes into the circuit and what comes out of the circuit. So the input, so if I draw the circuit for you, I happen to have which one where? The capacitor is on top and the resistor is here. Here's a resistor to ground. All right. And so as the circuit's drawn this way, this would be your V in, and this is your V out. In is always what comes in on the left, output is always what comes out on the right. And what are we attaching on the input on the left is an AC signal source. Right here is an AC signal source. That's what's being attached going in. And your V in peak, with a K or without it, with or without the K after the P, is what does this see in a peak voltage coming in. So if the source is 20 volt peak to peak, then your input is going to be half of the 20 volt peak to peak, which is 10 volt peak. Does that help clarify what we're talking about here?
Well, how does that differ from where it says VC peak?
Because it's a different value?
Yeah, I guess I'm just not really sure.
Yeah, we'll get there. Okay,
Okay.
we'll help you with that right now. But
Sure.
are we okay with the V input peak as being 10 volt peak?
Yeah.
Good. Okay, because we'll get to the VC peak in a little bit. VC peak is what we're going to measure across the cap. So the V input peak is going to be here, measured from this input tap with respect to what? Ground. This is outside of the cap. So black probe to ground, red probe to here. This is how we're going to hook up the oscope in order to measure what's going in. The voltage on the capacitor is measured this way. VC peak is measured across the cap. So it's a different connection point and a different value altogether based on where it is. Does that kind of help give you a preview what's going on with VC peak? Jess?
Yeah, it does.
Okay, yeah, so we're two different measuring points. VN peak is here between this tap and ground, and the capacitor peak is measured across the capacitor. So two different points of measurement, two different values. All right, so the next thing that you're asked for on here is the capacitor value we specified. So we happen to have capacitor value specified. Okay, move this up here so we can see this. Move this over here, we can see this better. All right, then we are asked for the capacitive reactance, X sub C. So the value of X sub C. Gregory, how do I find X sub C? I give you a formula right here, X sub C formula, 1 over 2 pi FC. So what do you calculate for X sub C?
I got 96.63 ohms.
966.63 ohms would be correct. And all you have to do is to take this value of capacitance and this value of frequency. Value of frequency is 4.45 kHz. You plug that into the denominator of this formula. So 2 times pi times the frequency times capacitance value. Reciprocate that, and you'll all end up with 966.63 ohms. The next thing you're asked for is impedance. So how do I determine impedance of this circuit? Carlos.
Sorry, Professor, I don't know off the top.
It's okay. Let's take a look here. If we've been playing with the exercises I've given you, you should be able to come up with a drawing. What would the drawing look like? Kirsten?
A right triangle.
A right triangle. So we would have a right triangle, and the right triangle looks like this. And the right triangle will have, on the horizontal, phasor, resistor at 2 k ohms, on the vertical phasor, X sub C pointing down. These are 2 ohmic quantities. I have 2 k ohms here, and I've got 966.67 ohms on this phasor coming down here. So 966.67 ohms. How do I add these ohms together? I can't add them together with straight math. I'm not going to do 2k ohms added with 966. I can't. Why? Because they're out of phase with each other. And I've done numerous PowerPoints and discussions as to why they're out of phase with each other. So we just can't add them up. But we can add them up using phasor math. Phasor math is easy because this is Pythagorean theorem. Hopefully it's easy. It is a right triangle. So we have to draw a right triangle. And so your Z stands for total ohms. Z is impedance. It is your total ohms. We calculate that as the hypotenuse of this triangle. And using Pythagorean theorem, we will calculate what value here, Ryan?
For
Z, impedance.
2.22 K or 2.22 kilo ohms.
Okay, we calculate 2.22 kilo ohms. That's your value of impedance. Very good. And does it make sense? Should the hypotenuse be a value that is greater than each of the legs? One leg is 2K, the other leg is 966.67, so is 2.22 kilo larger than either of the two legs? The answer is yes. Suppose your calculator spit out something smaller than 2 kilo. You've got a problem with your calculator, okay? All right, so once you have Z, once you know the total ohms of this circuit, how do we determine total current? Current question goes to, let's take a look here. Javier, how do I calculate current?
Ohm's law.
Oh, Ohm's law is good. So what do I do?
You divide voltage by resistance.
Perfect. Total current equals I, T. So you take your VT, divide by total ohms, ohms total. It won't just be resistance. We should say ohms. And so what's my V total here? 10 volt peak, yes? What is my total ohms? My total ohms is Z. So this is 10 volt peak, divide by the number we just calculated, 2.22 kilo ohms. And therefore, what current do you calculate for this, Anna?
I got 4.5 milliamps.
And works out to be 4.5 milliamps. 4.5 milliamps, okay? Now, you are asked for calculating the voltage of the resistor. So you are asked now for VR peak, and you are asked for VC peak. Remember, your circuit is like this, and you have attached to that circuit a signal source. The signal source is 10 volts peak. You're trying to find how much is here as VR peak, and you're trying to find how much is here, which is VC peak. So that being said, if you know the total current flowing in this circuit is 4.5 milliamps, how do I find each of these respective voltages? Don't we use Ohm's law? And once we get into AC, we should write Ohm's law a little differently. We should write Ohm's law as V, I, and ohm. Because in this particular part of our Ohm's law formula, ohms here could be an R, ohms here could be an XC or an XL, ohms here could also represent Z. So VI ohm is a better way of showing this once we get into AC circuits. So what we want is voltage across the cap, voltage across the resistor. Let's go ahead and start with voltage across the cap. If I want voltage from this circle formula, don't I cover V with my finger? And if I cover V with my finger, what do I have left? Isn't it I times ohms? So specifically, if I want VC peak, isn't that going to be equal to the current that flows through the circuit, which is I total? And we're going to multiply this by the ohms of the capacitance. Don't I have ohms of the capacitance? Isn't that my X sub C? So this becomes 4.5 milliamps times, what did we have here, 900 something? Yeah, 966.67 ohms. And that's my VC peak. So my VC peak is the product of 4.5 milliamps times 966.67 ohms. And the value, Chisamaga, do you have the voltage for this capacitor for us?
I got 4.37 volts.
Yeah, that's pretty good if we use the rounded numbers. My calculator, I use all of the memory pieces, and I get 4.35 volt peak. But if you got 4.37, I would certainly accept that. Any questions regarding VC peak? VC peak is this voltage across the capacitor. So this chunk of it is 4.35 volt peak up here. We start with 10, we lose 4.35 up here. Now, how do I find the voltage of the resistor? Don't I do the same thing? Isn't it still Ohm's law? If I cover up my V, isn't it still I times ohms? Well, what form of ohms do I have on this side of the circuit? Resistor. So it's I times R. What is my I? The I is this. And what is the R value? The R value was given in this case as 2 kilo ohms. So what is my VR peak in this particular case? question goes to, let's take a look here. Ephraim, do you have this voltage, please? Voltage across the resistor.
Yes. Let me see. 1 second. I have 9 volts.
I would have 9 volts here as well. So this is equal to 9 volts peak. Yes. What happens
That's correct.
what happens if we leave out the peak?
It's ambiguous.
It's not only ambiguous, it's incomplete. Yeah, but it is ambiguous because it's incomplete. All right. So if we leave out the peak, well, gee, is that DC? Is that RMS? Is that average? Is it peak? Is it peak to peak? It is ambiguous. So we have to specify if we're using peak current right here, and then this must be peak voltage.
Okay.
So you look at the schematic. You got 4.35 volts peak here. You got 9 volts peak here. And these two voltages, according to Kirchhoff, if you add up all the voltages in a closed loop, they have to algebraically add to 0. In other words, this add to this has to be equal to 10, yes? So you look at this, well, that's 9. You look at this is 4.35. That looks like it's going to be 13.35. How are we going to get 13.35 equal to 10? How do we reconcile that?
You have to take Pythagoras.
We have to think Pythagoras. You have to think Pythagoras. So the same way we used this triangle earlier for ohms, we have to use the triangle for voltage. So we do this to double check. So your VR peak is equal to 9 volt peak. And coming down in this direction is your VC peak. And the VC peak calculated to be 4.35 volt peak. These two phasors are out of phase with each other. You draw the diagonal between them. What happens when you add these two guys? Won't it be V total? And if you use the Pythagorean theorem between these two values, yes, this will calculate to be 10 volt peak, okay? That's how you double check and have confidence the values you put down here. And then when you go to measure this on Multisim Live, you'll be able to verify all of these numbers. 4.5 milliamps, 9 volt peak, 4.35 volt peak for the capacitor voltage. Last thing to do is going to be your phase angle. And how do I reconcile my phase angle? Question goes to Jess. How do I reconcile my phase angle?
I'm actually really lost on this entire process, but I'm going to guess it's also Pythagorean theorem, but I wouldn't know how to do it.
Well, it's here. Your phase angle is this angle of theta. How far down from the horizontal does this hypotenuse drop? Okay? And the same thing is true for this other drawing. The phase angle is right here, theta, because this is my starting point. My starting point is always my resistive phasor, and then going up or down will be my reactive phasor. My end point is here. So from my begin point to my end point, this thing will drop a certain amount of degrees because it's going to be a negative phase angle. That being said, how do I calculate the phase angle would depend on our memory tool. We go back to our memory tool, SOHCAHTOA, because we use SOHCAHTOA in order to determine our phase angles. And so if this is my angle of theta, you need to reconcile the names of the sides of these triangles. The longest side is always going to be hypotenuse, so that is my HYP. The other side that forms the angle, here's my hypotenuse, the other side that forms the angle, this is going to be my adjacent, so ADJ. And this side of the triangle that is way over on the other side from theta, this will be called what? Opposite. So the key thing here is to look at what are your original values of the triangle. 9 is one of the original values, so or earlier calculations. That starts with the letter A. And then the 4.35 was one of the other ones we calculated, and that is an O. A and O tell you which of these three names we're going to use. Which of these three names has an A and an O? It's going to be TOA. And what does TOA help us do? TOA, the T stands for tangent of angle theta is equal to, what's the O and the A? The O and the A says what's going to happen in the numerator, what's going to happen in the denominator. The O is going to be opposite, and the A is going to be adjacent. So there is my T right here. There is my O right here, and here's my A right there. That spells TOA. Now, we're not interested in the tangent of an angle. We actually want angle theta. And angle theta, if I move tangent from the left side of this equal sign, here's the equal sign. If I move tangent from the left side of the equal sign over to the right side, it becomes inverse tangent of opposite over adjacent. That's how you will find your angle of theta, by using what? So, ka, toa. Okay? Which can remind, as a reminder, you have to remember how to name the sides of the triangle. So,
Professor?
yes.
So whenever we're finding the phase angle, do we have to use the voltage values only?
Oh no, we can also do this with the ohms. It'll give you the same phase angle. If all your math is correct, the phase angle will be identical. So everybody do this, because this is a really good exercise. And get another piece of paper. Everybody do this. So we will do inverse tan of opposite, which is opposite over adjacent. And so in this case, this would be inverse tan of 4.35 over 9 volts. So if we use voltage, we'll do this. The alternative is we can do inverse tan of opposite over adjacent. And opposite over adjacent with our original resistor triangle, what was that? Here's theta, opposite is x sub c. So this is inverse tan of x sub c over adjacent, which is r. And x sub c was 966.67, and r is 2,000. If you do the inverse tan of voltages versus the inverse tan of the ohms, the angle will be exactly the same. And I'd like everybody to do that right now. Don't take my word for it. So on your calculators, everybody, the numbers are pretty straightforward. They're right here. Here's your calculator. Turn it on. Is your calculator on? Yes. Hit Shift tan. Everybody hit Shift tan. Then key in 4.35. Divide by 9. Oops, I need parentheses. Sorry. Back up. Shift tan. Open parentheses. 4.35. Divide by 9. Close parentheses. And when you hit equals in engineering, you will end up with some sort of a degree. So, Carlos Navarro, what did you calculate?
25.79 volts.
Degrees.
Sorry, it's the angle, right? You're right. Sorry, degrees.
So 25.80, because the 796, right? Doesn't your calculator show you 25.79? Yes. So you would round this to 25.80.
Correct.
And because this hypotenuse is going downwards, shouldn't this be a negative phase angle? Everybody.
Yes.
Yes, it should be a negative phase angle because the hypotenuse goes downwards. In other circuits, the hypotenuse may go up. In everything we've done, the hypotenuse comes down. So don't forget negative. Now let's try.
Can you explain that?
Why it's negative?
Yeah, I don't get it.
Okay, the reason why it's negative, I'll show you here, and I showed this on Tuesday, but I'll be happy to show it again. It's all right. And let's go here, and let's go here, and let's do this, and find my week 7. No, it's week 6 is where I put it. Week 6. number 2. Okay, and let me go ahead and all right, let's go ahead and start there. Let me do the share here and here. Okay, so we say that IC and VC are out of phase with each other. Why are they out of phase with each other? They're out of phase with each other because of how the capacitor charges. Remember, capacitor current is at maximum. The instant we close the switch, current is at maximum, but the voltage is at 0. And it takes a period of time for the capacitor to reach full charge for a full voltage. In this case, for the circuit that I had, was 12 volts. The current, maximum current of the circuit starts at 2.55 milliamps, but over 5 time constants, it slowly diminishes down to 0 current. Because when this reaches full charge, no more current flows in the circuit. So there is a phase difference between when voltage is at maximum versus when current is at maximum. So we use the RC time constant chart to show us these curves that demonstrate that they are out of phase with each other. I use a multisim live. I have a AC source, and with an AC source, I go ahead and put in a capacitor, and notice that the ammeter is placed here at the top of the circuit. The voltmeter is placed over here, and ground is here. So what happens is we can see that the current phasor, which is blue, is not peaking at the same time that the voltage is peaking. They are clearly out of phase with each other in this drawing. So as they are out of phase with each other, we have to take a look and see how far apart are they. So if we put the cursors where you have done this in several examples, or have seen in several examples, I'm going to put this C1 at as close as I can to the where the green waveform crosses the 0 line, so that's why I have a dot there. And I'm going to place cursor number 2 where the blue waveform crosses the 0 line, which is right here. And I read the time between the two, and I read this, in this case, very close to 25 milliseconds. If I take 25 milliseconds, that is the phase shift between these two waveforms, right there, it's close to 25 milliseconds. And I divide that by the period of 100 milliseconds, and then I multiply that by 360 degrees, which is the rotation of a waveform. The entire waveform is 360 degrees. I'm able to determine that the phase shift here, these waveforms are 90 degrees apart. Okay, that current and the voltage through the resistor, voltage across the resistor and current through the, back up, the voltage across the capacitor and the voltage of the voltage of the capacitor and the current of the capacitor are 90 degrees apart. I should read what I typed. Cursor C1 shows current peaking at 90 degrees before cursor C2 shows capacitor voltage. Now this is with respect to waveforms. And why are they out of phase? Because of RC time constants. That's why they're out of phase. Now, how does this relate to the phasors that we draw? This relates to the phasors that we draw this way. Remember, a phasor is nothing more than a vector that is rotating on this axis of 0 degrees to 90 to 180 to negative 90 back to 0. So a phasor is a rotating vector. My IR right here, IR and VR, they are in phase with each other. For resistor voltage and resistor current, they are in phase. That was demonstrated here. When I have just a resistor in the circuit with a AC source and I go to measure with an ammeter and a voltmeter, notice that both of these peak positively at the same time. Both of these waveforms peak negatively at the same time. They both cross over the 0 line exactly the same time. Therefore, these are what? How do I call this out? They are said to be in phase with each other. That's why the phasor diagrams have them both pointing in the same direction. If I superimpose these together, both of these going together, I can do this diagram here. Your capacitor with the resistor doesn't work this way. Your capacitor, as we've already discovered, is out of phase. You've seen this picture before. How do I draw their phase relationship using phasors? I draw their phase relationship using phasors, showing that on this circle, if I start with my current phasor, it will have rotated all the way up to 90 degrees before my voltage phasor even exists. And that's shown here. The current phasor is the one that was in blue. It's peaked 90 degrees before the voltage phasor even exists at peak. So that's why I can draw the arrows 90 degrees with respect to each other. So they're clearly out of phase. It has been, what word did I use here? It's rotated to a positive 90 degree position while VC phasor is still at 0. Are we okay with this diagram of phasors being showing us this phase relationship between the waveforms? Okay. Once we put them in a circuit together like this, here I have a capacitor, here I have a resistor. What is the same in a series circuit? Any series circuit.
Current?
Current's the same. So now I can't just superimpose this set of phasors on top of this as they're drawn, because current here is pointing at what degrees? For resistors, it's pointing at 0. What is current pointing at here in this lower diagram? Positive 90. I can't just superimpose this on this and try to work out some kind of triangle. Ain't gonna work. So what I do is I'm gonna rotate this guy, and I demonstrated rotating this guy. I did this last week. I'll do it again. Right here on the camera, stop this share. Right here on the camera, here is my IC pointing up at positive 90 degrees, yes? I have to get this pointing at 0 degrees because resistor's pointing at 0 degrees. What do? I rotate this puppy like so. Now my IC phasor is pointing at 0 degrees because 0 degrees is the horizontal, yes? But which way does this force my voltage, my VC voltage to point? Down. And all that occurred was this relationship from the previous drawing that we had, because I need this phasor pointing in the same direction as IR, I have to rotate it this way, which means VC is going to be pointing down. So that's why anything with a capacitor in series will have a negative phase angle. Let me continue this. Right here. So now do I have in this drawing my current phasors shown in pink pointing at 0 degrees. And as this is pointing at 0 degrees, remember my voltage VR and IR, they're in phase with each other. But what happened to my...
You're not sharing your screen.
I'm sorry, you're right.
It's okay.
Thank you. Let me come back to here. So sorry. Okay, so now as we go back to this drawing, my pink phasors are my current phasors. Do I now have my I resistive current and my capacitive current both in phase with each other pointing at 0 degrees? Because in a series circuit, current is the same. These pink ones have to point in the same direction. So what am I left with? Which way is my VR phasor pointing? 0. Which way is my VC phasor pointing? Negative 90. When I put these two together, this is what I have. And what happened to my current phasor? Well, because these two are equal to each other, as I wrote down here, because they're equal to each other, what happens to them? They can cancel out. What does that leave me with? 2 green phasors. Resistor pointing to 0, VC pointing at negative 90. Are we okay with the transition from here to here? So the last thing for us to do is to make this into a triangle. And to make this into a triangle, all I've done is take this guy and attach it to the end of the first one, and I end up with this guy over here. So from the point of origin, right here, we follow the resistive phasor at 0 degrees, then the VC phasor comes down, and my hypotenuse is going to result with a theta that's going to be pointing southward for a negative phase angle. Does this help you? Does this help solidify why in this particular instance the phase angle is going to be negative?
Yeah. I And I remember going over this. I guess I just didn't really walk away with the understanding that they're always going to be negative, or at least for this course they are. Is that true?
No. They're always, for this circuit, they're always going to be negative, but for other circuits, they're not. Yeah, you have to look at, and it's very easy to decipher which way the angles are going to be, as long as you understand Eli the Iceman. Everything hinges on Eli the Iceman, because Eli says in no uncertain terms, and that's why it's the very next slide. Eli the Iceman says, C stands for capacitance. And anywhere where you have a capacitor, current will lead voltage by 90 degrees. And since we don't have the time to talk about a parallel circuit between a capacitor and a resistor, we won't have any positive phase angles to talk about. Since we're not taking the time to talk about RL circuits, series or parallel RL circuits, we won't talk about anything that will reflect a positive phase angle, but there are certainly going to be positive and negative phase angles. It depends entirely on the circuit that you are given. But how do you decipher whether the angle is going to be positive or negative? You can always come back to this derivation. This derivation is rock solid. That based on these waveforms, these two phasors are in phase. Based on these waveforms, they're 90 degrees out of phase. How do we add them together? Depends on the type of circuit that we have.
Okay.
Okay.
Thank you.
You're welcome. I think, do I develop that all the way to the very end? Yeah, to the very end, I have a parallel phasor. And a parallel phasor gives you a positive phase angle. Right here. Because what do we have to align? What's the same in a parallel circuit? What is the same? Isn't
Voltage.
VR and VC the same if they're in parallel? So if voltage is the same, don't we have to have the green phasors pointing in the same direction? The answer is yes. So where does that leave your current phasors? It leaves IC pointing up. Okay.
That makes a lot of sense. Thank you.
Okay. So if nothing else happens, copy this PowerPoint that I have and take it with you, and you will never ever have any problems with reconciling positive phase angle, negative phase angle. What do I do with this? As long as you remember your fundamentals, and the fundamentals go back to this slide right here. In phase, out of phase by 90 degrees. Which one's leading? Current leads for capacitors. In an RL circuit, we have a different ball game, and we're saving that for another semester. Good question. I appreciate the question. Hopefully this helps bring a little greater clarity as to why we're dealing with negative in this particular set of circumstances. All right, moving right along. So we happen to have this, and we calculate the angle. So I'm still looking for a numeric value for the, oh, we have the numeric value, negative 25.80. And if we do the math right here, sorry, let's have you see what I'm pointing at. I apologize. Okay, so as you're looking at what I'm pointing at, the question is, we already calculated a negative 25.80 degrees using voltages. Let's confirm that using the ohms. The ohms were from this triangle. We want to calculate this phase angle of theta. How far does the hypotenuse swing down based on these numbers? So opposite is 966.67. Opposite is the number that goes on the top of the fraction. And the adjacent is what goes in the denominator, is 2000. So everybody do this. Shift tan, open parentheses. Shift tan, open parentheses. Your 966.67 divide by 2000 and close parentheses. Hit equals. Exactly as I have written, exactly as you key into your calculator. And the question will go to, let's take a look here, Kirsten. What do you calculate? Are you there, Kirsten? Harpreet, what do you calculate?
25.80 degrees.
Does it have a polarity if the phase angle is pointing downwards?
Negative.
So the answer is going to be a negative 25 point, what did you say?
25.80.
25.80 degrees. Wow, we calculated that number of degrees using voltages, and we calculate the same degrees using ohms because our triangles are identical except for one is measuring ohms, the other one is measuring voltage. So you can double check. You can use either triangle. Was an earlier question, do we do this with voltage or do we do this with ohms? You could do it with either one. You better end up with the same phase angle. Any questions on page 5? Okay. Page 6. So you're looking at Pythagorean theorem exercises on page 6. So let's go ahead and see what you got. Question goes to Toan. What's your value for the first triangle? We're looking for impedance for the first triangle.
Z equal 1.67 k ohm.
Z is equal to 1.67 k ohms. Let's see if that's even possible. So if one leg is 1.35 k and the other one's 988, and you say 1.67, is 1.67 on the hypotenuse greater than the legs? Yes, it is. So it's a plausible number. 1.67 k ohms is correct. Good job. Next question goes to Luis. What's my second triangle in terms of resistance? Luis. Gregory, what's my second triangle?
I have it at 296.03 ohms.
And should it be less than the hypotenuse?
Yes.
Yes, it should. Hypotenuse is always greater than the legs. So if you calculate something less than the hypotenuse, it's very plausible. And it is 296.03 ohms. Anybody have any questions regarding that? So far, so good? Okay, the last triangle. Oh, there's no last triangle. All right. So that being said, oh yeah, for the left triangle, we have impedance. Oh, phase angle. Yeah, we need to do phase angles. So phase angle for the left triangle. Luis, are you back now? Could you give us the phase angle for the left triangle?
I got 53.8 degrees negative.
Okay, because this is coming downwards, this will in fact be a negative 53.80 degrees. What happens if you leave out the negative, my friends? It would be half wrong. Okay. The next one, how about the phase angle here? The phase angle here, this one goes positive. So here's an example of a positive phase angle. Jess, what do you calculate for this guy?
I don't know.
Okay, so phase angle here, let's do this exercise. If this is my theta, can you call out the names of the sides of this triangle? So Jess, help me out. What do we call the long side of the triangle?
The hypotenuse.
So that starts with the letter H. So HYP, yeah?
Yeah.
Okay, and the angle's here. So what do we call the side that helps to form the angle with the hypotenuse? What do we call this side, Jess?
Adjacent.
Adjacent, so ADJ, yes?
Yeah.
So all that's left is OP. So OPP is over here. So what's given? What's given is 433. 433 is on which side, Jess?
Hypotenuse.
Okay, so we clearly have an H component. So here's an H component. What else is given is the 316. The 316 is which side of the triangle?
Opposite.
Okay, so we have an H and an O, yes? H and O. So if we go to our friend SOHCAHTOA, the sides that have the initial values, you called out correctly. You look at the very first letter of what you've called out. Hypotenuse starts with an H, opposite starts with an O. So the H and the O are the clue to you as to whether we use so, ka, or toa. H and O, what do you think? Which part of SOHCAHTOA are we going to use, Jess?
So.
So. And what does so mean to us? So means, so, S-O-H means, what does the S stand for?
Sine?
Sine, yes. And we abbreviate that as S-I-N, but it is technically S-I-N-E. Sine of angle theta is going to be equal to something over something. So the first letter tells you which trig function we're going to use. The trig function is going to be sine. The O tells you the numerator, and the H tells you the denominator. So what is my numerator? What side of the triangle?
The opposite?
Opposite, all right, OPP. And then the H is in the denominator, and H stands for?
Hypotenuse.
Exactly. So that's what we do with SOH. We determine we're going to use SOH because O was one side and H was the other side. We're going to use SOH. What does SOH tell us? SOH tells us mathematically sine of angle theta, because here's the S right there, and here's the O, and here's the H. So it tells you how to set up your formula. Once you know whether you're going to use so, ka, or toa, once you know how to write out the formula, now the rest is academic. You just have to pop in the numbers. And we don't care about the sine of an angle. We want angle of theta. So how do I move the sine function from the left side to the right side?
Reciprocal.
Mathematically. Exactly. It becomes the inverse, yes? Inverse sine. It's the reciprocal key. It's not the reciprocal key of the calculator we hit, but it is a reciprocal function. We call this inverse sine. And then this will be in parentheses. Opposite for this second triangle is what value?
316.
So 316 over, and then the H is what value?
433.
Precisely, 433, close parentheses. And so now you've written you've decided you're going to use so. You're going to write out the equation that so tells us to write. You're going to fill in the equation, shifting the trig function to the right-hand side. Now we have to key this into the calculator. So when we go to key this puppy into the calculator, this will be shift sine to give you the inverse sine function, open parentheses, 316 divide by 433, close parentheses, and hit equals. And with utmost confidence, what do you calculate?
46.47 degrees.
46.47 degrees. So it is in units of degrees. And is this a positive phase angle or is this a negative phase angle?
Positive.
Why is it positive? Because the hypotenuse is swinging above 0 degrees, right? It's swinging upwards. So this is a positive 46.67 degrees. Are we feeling a little more confident about this process?
Yes, thank you.
You're very welcome. I don't want to leave anybody in the dust. All right. Any questions at all about triangles?
Yeah, I have a quick question. So for the second triangle, like we have to use sine. We have to use sine, right? Even though,
no,
like,
you don't have to use sine. No, that's a really good question, Abbas. You don't have to use sine. You want to start off whenever possible with the given values, but could we use the 296.03? Heck yeah, we can use any combination of two sides to calculate the same phase angle. All right. So let me prove that to you this way. I'm going to flip this paper upside down. And now what I want to do is I want to use different sides. I'm going to use this one, and I'm going to use this calculated one. Are we okay, Abbas? That's a good question. I appreciate you asking. It's a really good question. So here, if this side is of interest, this is the long side. What do we call this? This is called what, Abbas?
the hypotenuse.
Hypotenuse. So that starts with what letter?
H.
All right. And we decided we're going to use this side, and because this helps to form the angle, this was called what side of the triangle?
Adjacent.
Which starts with what letter?
A.
So here we have an H and an A. So I have an H and I have an A, yes? So you look at SOHCAHTOA. Which of these three trig functions has an H and an A?
Cosine?
Yeah. So if we use adjacent and hypotenuse, if we use those two, we're going to use CA. Is that correct?
Yeah.
And if we're going to use CA, watch how this works. CA says what? The cosine of angle theta is equal to, what's A over H? A stands for what?
Adjacent.
So adjacent goes in the numerator. H stands for?
Hypotenuse.
And that goes in the denominator. So now has that evidenced a C, an A, and an H? So far, so good?
Yep.
Now, we're not interested in the cosine of an angle. We only want the angle. So if I move cosine from the left side of the equation to the right side of the equation, what does this become? How do I call this out, Abbas?
Inverse a cosine.
Inverse cosine, precisely. And in parentheses, what is the value of my adjacent?
296.03.
296.03. And what is the value of my hypotenuse?
433.
433. Close. Now, to key this into the calculator, same idea. You do a shift cosine, right? It's not shift tan anymore. It's shift cosine. Open parentheses, 296.03 divide by 433, close parentheses, and equals. When you go to do this, everybody, shift cosine, open parentheses, 296.03 divide by 433, close parentheses, equals. Now, as I called it out twice, everybody should have done this calculation. Remember, this is a participatory exercise. You are not a fan sitting in the stands. So I am looking for a number from Chisamaga. Give me a number here. Chisamaga.
Yeah, I'm putting into my calculator right now. I still have to.
Shift cosine, open parentheses, 296.03 divide by 433, close parentheses. What do I get?
46.87.
And after engineering, 46.87 is what that, oops, you can't see it, sorry. 46.87 is what you would write down on a piece of paper. And isn't that the same value we wrote down earlier, yes?
Yeah.
So you can use, if you haven't learned this in geometry class, because this would have been taught in geometry back in middle school, or certainly by the first or second year of high school. I remember teaching this to ninth graders. So if you didn't learn this in the ninth grade with your geometry instructor, please be reminded you can use SO, CA, or TOA for this exercise. You're not stuck with just using one math function. And if your numbers are right, you can use any combination. You could use SO, CA, or TOA, and you will always, always end up with the same number of degrees if your values calculated correctly. Okay? Any more questions regarding triangles? Okay. The next question has to do with an RC circuit. So as we're looking at an RC circuit, you are asked to, again, decode a capacitor value. There it is. You got to decode the capacitor value. So 785 decodes to be what capacitor value? Question goes to Erica. What do you got?
I got 7.8 microfarads.
And it works out to be 7.8 microfarads is correct. What happens if that number is wrong, my friends? What happens if we decode the first value of this sequence of calculations incorrectly? almost everything else will be wrong. So you've got to make sure you are confident in decoding your capacitor values, okay? Because if this one's wrong, everything else is south. Do not rush. What's the next question? The next question asks you to calculate gray, orange, black, silver at what? Minimum tolerance. So what is my R value? R value. Ephraim.
That is 74.7 ohms.
How many people agree with 74.7 ohms? Give me a thumbs up or some kind of indication. Speak up. Javier says a thumbs up. You only got one. Oh, two people. All right. 74.7 ohms is correct. Does anybody have any questions how to calculate maximums and minimums for resistances? I take that as a no. All right. So what happens if the first value is wrong? You're going to have problems. What happens if the second value is wrong? Your minimum or maximum is calculated incorrectly. You're going to have issues. Yes.
This Carlos, just like on the cat value, just really quick. So I got if I'm trying to decode it right, 7850. Does that sound correct so far?
7850 as I'm writing down for you. Yes. Then followed by what?
Okay, that's a step I'm missing. What do I do? How do I?
Okay. It's always going to be some units of farads. What units of farads goes in here? It's always the same one.
Right.
Do you remember? It should be in your notebook because you can use your notebook. It's right here. Picofarads.
Okay, yes. Got it. Okay. That's the P.
Yeah, anytime we're coding 3-digit codes for a capacitor, it's always coded into picofarads.
I'll make sure it's super visible in my notebook. Thanks.
Okay, make sure it's super visible in your notebook. And what you got to remember is when you key this in, 7, 8 with these zeros, what 10 power is a pico? 10 power is a pico, 10 power of what? And again, that table should be in your note, in your journal as well.
Pico's -12, right?
-12, correctly. So when you enter this, followed by 10 -12, you're going to end up with 74.7, 7.8 microfarads. Okay?
Thank you.
You're welcome, sir. I appreciate all the questions. All right, so resistor at maximum or resistor at minimum, you have to know with confidence how to do your resistor color coding. Then when you have the two, do we have enough information to be able to calculate ohms of the capacitor? Because this is an AC circuit. So as this is an AC circuit, we're going to do analysis. How do we calculate ohms? There was a formula to calculate ohms. There was a symbol for ohms. What do we do there? Question goes to Javier.
Could you repeat the question?
I need the ohms of the capacitor. How do I do that?
I'm not sure.
Okay. Ohms, cap ohms equals something called X sub C. They're giving you a clue. So how do I find X sub C?
The formula
is
1/2 pi FC. And so F would be 3.6 kilohertz, and then C would be 7.8 microfarads.
Precisely. So 1/2 pi and multiply by 3.6K and multiply by 7.8 micro. And as long as you do the math properly, you will have a value for X sub C. And so your calculated value for X sub C, my friend?
Hold on. 5.66 ohms.
Okay, which would round properly to 5.67 ohms. Okay? Be mindful of that. 5.666666 will round to 5.67 ohms. So these are the ohms of your capacitor. So guess what? You have a phasor going in this direction, the R phasor. R is equal to, what do we calculate? 74.7 ohms. Then coming down in this direction is a little tiny phasor, of X sub C, and X sub C equal to 5.67 ohms. And these guys are 90 degrees apart. So your job is to calculate total ohms. So total ohms, we will call this Z. What is Z? Z is impedance. So how do I do the math to calculate the hypotenuse of a right triangle? This squared plus this squared is the sum, do the square root, right? Isn't Z equal to the square root of xc squared plus r squared? And when you go to do that, it won't work out the mechanics with you. You should be able to do that. The impedance will calculate to be, Harpreet, what value of impedance do you get?
Yeah, give me.
Greg, what value do you have?
74.91 ohms.
74.91 ohms, okay? 74.91 ohms. And 74.91 ohms is correct. Should be 74.91. All right. The next thing that you're asked for is total current. Because doesn't Z represent total ohms? Isn't impedance equal to total ohms of a circuit? You have resistive ohms, you have capacitive ohms, reactive ohms, and so the total ohms is called impedance total. So do we have enough opposition to current based on this 15 volt source that we should be able to calculate what our current will be? The method is to use Ohm's law. So what value of current do you calculate? Question goes to Ryan. Do you have the value of current?
I got 221 milliamps.
Okay, I have a little more memory space in my calculator. I get 200.23 milliamps because I'm not using rounded values for impedance. So you get something close to 200.23 milliamps. We're pretty happy. Any questions on the total current? Once you know the total current that flows in here, once you know your IT, and IT is 200.23 milliamps. Do I now know the current that flows through the resistor? Do I now know the current that flows through the capacitor? Do each of these have ohms? This guy has ohms. The ohms on the resistor we calculated at 74.7 ohms. The ohms of the capacitor we calculated as 5.67 ohms. If you know the current going through ohms and current going through ohms, can we calculate each of those voltages? And so the next value that you're asked for is the voltage of the resistor. So how do I find the voltage of my resistor? Question goes to Chisamaga. How do I find the value of voltage across my resistor?
You take the current and then you multiply it by the resistor value.
Precisely. It's Ohm's law. So my VR is equal to my IT times R. And we just calculated IT as 200.23 milliamps. We're going to multiply by the R value we determined earlier, 74.7 ohms. And what is my VR going to calculate to be, Chisamaga?
14.95 volts.
That works out to be, yeah, that's fine. I calculate 14.96 volts for VR. So now do I have a voltage across the resistor that I'm I should be fairly confident with. I didn't ask you for a VC, but you should be able to calculate a VC as well. So VC is equal to I total times what, C? No, times X sub C. I times ohms. So this is equal to 223 milliamps. We're going to multiply this by a little tiny 5.67 ohms. And when you go to do this, this will calculate your VC as being 1.13 volts. Now you have a VR and you have a VC. How do we know these guys are right? Is there a way to double check this? How would I double check this? How could I double check this?
Pythagoras theorem?
Pythagorean theorem. So we should remember, the same way we drew the triangle earlier for the ohms, we should be able to draw the triangle for Pythagoras, for voltages. So I would have my VR of 14.96 volts. And right down here, I have my VC of 1.13 volts. And I want from the origin to my destination a hypotenuse, which is my V total. So if I do Pythagorean theorem to calculate the hypotenuse, this should give me back my 15 volt source. Okay? I won't take the time to do that now, but that's how you double check these numbers. So the last question on this exercise is theta. There's theta, why? Because that's your point of origin. Theta is always related to the part of the triangle that's your point of origin. So you're looking at this guy coming down. So is theta going to be positive or negative in this case? Negative. And how do I go ahead and do this? So with confidence, Jess, tell me how I'm supposed to do this.
So we could use any of the so-called TOAs because we have the voltages for each side.
Precisely, because we have all three values. We have this guy, and this guy. Pick two sides.
I chose to use Ka.
Okay, so Ka, so A and H, yes?
Yes.
So here I happen to have H for hypotenuse. Here I happen to have adjacent. So if we're going to use adjacent and hypotenuse, there is the A and there's the H, which if we go back to SOHCAHTOA, it tells us use Ka. And if we're going to use Ka, why Ka? Because I have an A and an H, because these are the two sides. We could use any of the sides, but these are the two that your classmate picked. So cosine angle theta is equal to the A over the H, adjacent over hypotenuse. Angle of theta is inverse cosine of adjacent over hypotenuse. So this is equal to shift cosine, open parentheses, and adjacent is 14.96 over the hypotenuse of 15, close parentheses, and equals. If you go through this sequence with confidence, Jess, what do you calculate the angle to be?
I think I made a mistake on mine because I have 4.29 and that's not right.
Well, I don't know, maybe not. Let's try this, because it's a very narrow angle here, and it's tiny. Very possible.
I think I might have mixed amps and volts in my numbers, though.
Oh, well, let's recalculate this. Let's go ahead, do a shift cosine, open parentheses, 14.96, divide by 15, close parentheses, and equals.
4.19 degrees?
4.19 degrees, and since this comes downwards, we have to do what?
Negative.
Negative 4.19 degrees. And we'll see what the magic paper says. Pretty darn close. I have more memory space in mine, so it works out to be negative 4.34 degrees Since this is the last calculation of a sequence, I would certainly accept your 4.19 degrees, simply because the 4.96 is a rounded value. Okay, very good. And period and frequency. Frequency is given, period is a reciprocal. All right. Any questions on that part of page 6? Okay, the last part of page 6. Yeah, you're asked to verify with Multisim Live. And yeah, if you've gone to do so, then everything else is good. All right, any other questions on the practice final? So in addition to these items on the practice final, there were exercises in the, were posted for transformers, and also exercises posted for superposition theorem. And anybody who attempted those and uploaded those before 6 o'clock this evening can earn up to an extra 50 bonus points. And I see that at least 6 or 7 of you did. I'm very proud of you guys. You guys should be proud.